Hi everybody. This is John Robert Huck who's here. Shasta who's currently in India. I'm in, I think, in Colorado or Oregon. Oregon, yeah. Okay, good. This talk, I try to make this extremely non-technical. So I hopefully, I put up a few open questions, so maybe this is something that we can all talk about and excite some of you guys. Okay, so here is. Okay, so here's this famous problem. Everybody's heard of this, hopefully. I want to multiply two matrices. I give you as input, and I have this trivial and key algorithm. But we're all like 900 people, so we kind of have this notion of class MM. There's some notion of omega, and like over time, we've slowly been improving this till kind of there, right? And I think this is like a hard problem. Like I'm inspired by like Moby Dick, where like I think of MM as like this big whale, and I try to make this topical. Where it seems like a really hard problem to solve. So we should maybe like try like at least for me to think of easier problems and hopefully maybe see if we can get some insight there and maybe build our way up to these harder problems. Okay, so what's an easier problem? Let's look at just the verification question, which is I give you three matrices A, B, and C, and my goal is now to compute. It's just to verify whether C is actually the product of A times B. Oh, Josh, this is like you're finished. So I put you and Yuntan. I mean, normally the changes on where I'm giving the talk, but like, fortunately, it's always the head. All right, good. So I want to solve a verification problem, which is I have three matrices A, B, and C, and I want to verify that C is the product of A, B. Okay, and again, like there's a trivial and the mega algorithm, I just brute force, and I look at every entry. So we can ask, can we solve this faster? Some of you probably know. If I'm allowed randomness, I can. And this is like Peebles' algorithm, it's known 50 years ago. How does the algorithm work? It's a very simple observation. If I want to check two matrices are equal, I just am checking if AB minus C is a zero matrix. And to do this, I can just multiply with a random vector, and that kind of catches a non-zero point with high probability. So if I repeat this a few times, I'm able to check in n squared time that like the two matrices are equal. So verification has a fast randomized algorithm. Can we solve it? So I guess the natural question is, can we solve this deterministically? Right? So can we kind of approach MMB and like come something better than omega deterministically? Okay, and so kind of the first result is the following. If I give you three matrices and like the product AB disagrees with C on a sparse set of points, so just like n to the 2 minus epsilon, any subquadratic number of points, then there's a deterministic algorithm that runs in less than n to the omega and solves for it. We decide whether or not this begins. Okay. So I'll give a few helper problems, then I'll rephrase this in a different way. I think it'll be a little bit more intuitive. Okay, so the first problem I'm going to say is that for the rest of the talk, I'm going to solve the problem that A times B is equal to 0. I claim that this is equivalent to verification. Why? Because there's a very simple reduction where I can convert my verification question into AB equals 0. Because when they're equal, this thing on the top left would be 0. AB minus C would be the same. Okay, so for the rest of the talk now, we're going to solve. I give you two matrices and I want to check if their product is 0. This maybe most of you know, but I'll still keep it. So the idea is going to reduce our algorithm to fast rectangular MM. And fast rectangular MM is just saying that I have some big matrix and I have like a slice of a matrix where K is something between 0 and 1. And the main takeaway is whenever K is less than 1, my running time is less than omega. So if I can reduce my problem to something where I have like omega 1 K1 where K is less than 1, then I get like a faster than omega algorithm. Yeah, so this is just okay, good. So really the key insight for this is the following observation, very, very simple observation. If a matrix is n to the delta sparse, so think of delta as anything between 0 and 2, right? So if it's 2, it's like a dense matrix. If it's like less than that, it's a sparse matrix. If my matrix has n to the delta non-zero entries, then there exists either a row or a column that's non-zero and has at most n to the delta over 2 non-zero elements. So there exists like very sparse row. And this is a very easy proof. I mean, if every row had like high sparsity, then if I look at the columns, they must be, they can be mostly sparse. Okay, good. So now we're ready. We have almost everything we need. So I'm going to redefine our problem. So I give you two matrices A, B, and I want to solve the following case. I'm promising you that there are at most n to the delta non-zero entries in this product. Now tell me whether it's the 0 case, where the product is 0, or I'm in the case where I have at most n to the delta non-zero points. So distinguish these two cases. Okay. And we can now like apply our sparse matrix lemma, and we're promised the following that there must exist in my product one row or column that is n to the delta over 2 sparse. Okay, so the question now is just, can we detect such a sparse row or column? I give you AB, can I detect such a row in my column? If I can do this, I'm done. Okay, so how do we do this? Like this is kind of the question, and this now is we're gonna use the magic of arithmetic codes and get this for free. So let me quickly kind of define arithmetic codes here. All we need is that there's some generator matrix that maps my code word, like my message, to some bigger space. And I have a parity check matrix that can detect, like if it is a code word, it outputs the product of my parity check matrix times my code word is going to be 0, otherwise it's going to be non-zero. And if my code has some distance, I'll show a picture, it'll make more sense in a second. If my code has some distance properties, I can kind of embed a sparse row into, like, if my distance is longer than the sparsity of my vector, then I can guarantee that like my sparse vector will not be a code word. And so my parity check matrix will detect it. So let me maybe give a picture here because I think it'll be easier. Well, how does a linear code work? I have some like small space, like some message space, which is on the left. I apply my generator matrix, which is just a matrix, on it, and I look at a bigger space. The power of this is now when I'm in my big space, I have some more structure. I'm embedding my small space into the big space. And now my code words, right? I can guarantee with my code that the distance is going to be so the distance between any code words is at least d, right? And so if I have this, I can also like correct errors within the over 2 handling way of my string. Okay, so this is all a lot of words. Why is this useful? Well, if my distance was like kind of, so think of my sparsity vector, right? I have a sparse vector. My 0 is a code word, right? The 0 string is a code word. So if my sparsity is less than my distance, then my sparse vector cannot be a code word. And so my parity check matrix will just catch this. And the whole point is my parity check matrix is of low dimension. So now I can just multiply my matrices and I get like a low dimension. I have like a continuous fast rectangular solver. So again, I just pick I find the code with sufficient distance bigger than my sparsity, and then I just multiply it with my AB and AB transpose. And the point now is that I can actually compute H times AB fast because this is a rectangular notation. And okay, so if you don't like codes, you can even like think of H as just a random matrix. You don't really need codes, but you will see why like thinking of this as codes is a useful perspective to solve the problem. Okay, question. So just blindly applying parity check matrices to the black box, I can already just get deterministic MMB per sparse vector. Question.
So, yeah, to make sure I understood correctly. Intuitively, you're solving the Cartlet case, right?
Good, that's the next slide. So intuitively, what is the hardest case? Yes.
If you're illegal, then it's easy.
Yeah. So, and that's exactly the next slide, which is like, if you think about it, the hardest case seems to be the case where they disagree on just a few points. Because I have to find where they disagree. This seems like a naturally harder case to solve. What we're saying is that the opposite is true. The hardest case, the case we don't know how to solve, is a case where they disagree on many points. So I mean, we're not the first people to point this out. Like Kuhneman kind of showed this first in 2018, where he said that if my matrix has like n to the 1.36 sparsity, then I can detect this. We kind of are like generalizing this all the way up to subquadratic, right? And this is really counterintuitive because exactly what you're saying. The hardest case of the deterministic algorithm is when I disagree on many points. And for this case, I have a very trivial randomized algorithm. I don't even look at the matrices. I just sample, a constant number of points, and then just look at the dot product of those points. So exactly, like in some ways, we're showing that the hardest case is actually the easiest for the randomized algorithm, which is, I guess, like pretty counterintuitive. Okay, and so maybe like it's like you have this like big mass like that's hidden in your matrix, but like there's no witness to verify this. It's like this seems like a very, whereas if there was like a small thing, you could actually catch it. It seems kind of counterintuitive. Maybe okay, and so like this is like the most natural question now, which is here's the open question. I give you two matrices AB, and I give you the following promise. Either the product AB is equal to 0, or AB has like epsilon n square non-zero entries in the product. Distinguish case 1 from case 2. If you could do this in partial kinetic omega, then you kind of already de-randomized P1 partially. Question. Alright. So this is warm up. So let's now kind of ask, like, if you look at the algorithm so far, we didn't really do anything about error correcting purpose. So we used the factor as a parity check matrix, but we didn't like actually use anything else. We didn't use any decoding, we didn't use anything else. Like we kind of like we barely touched the surface of what we could do, right? It's like almost using a heavy hammer for something really small. So can we like kind of get more out of, codes? And turns out we can. So if you think of MMV as the decision version, you can solve the search version, which is just MM. So if I give you two matrices A, B, and I promise you that the output is sparse, and only enter the delta non-zero entries, then I think that there's a deterministic algorithm, and its running time is the same as the MMV running time. So there's a search and decision reduction. I can solve the search problem, which is actually MM, when my output is promised to be sparse. So we'll call this output sparse enough. Okay, so let's see. And just to kind of give, like Nick has an algorithm, like from 2 years ago, where they give like, there's a faster randomized algorithm. You could think of this as maybe like a de-randomization or like this, a different. So that you can see that one is a little bit faster, where my exponent is 1, 1 delta minus 1. Ours is 1 delta over 2, 1. But ours is deterministic, theirs is randomized. We prove all results over like any prime field, but you can generalize it to any integer. Okay. Questions before we do this? Awesome. Okay. So I think let's kind of the inspiration comes from compressed sensing. So what is compressed sensing? Let's quickly recap. I have three parameters: M, N, and T, and M is less than N. So the idea is you find like either a compression or a measurement matrix H, and recovery algorithm with the following properties. If I give you any sparse vector E, my recovery algorithm, when I use my compression matrix to compress my sparse vector to a dense small space, and now my recovery algorithm can extract the sparse vector algorithm. Okay, so that's what compressed sensing is, and like now, like what we care about is some kind of fine-grained version of this. So we'll see in a second. So again, I take some compression matrix. It takes a sparse vector E, and it compresses it to a dense vector S of smaller dimension. And then my recovery algorithm can extract from S E. That's what compressed sensing promises. Like that's the promise of a compressed sensing scheme. So we could design kind of a nice compressed sensing scheme. We'll probably be able to extract a search algorithm for a minute. Okay. So let's live in a special case where every column of a product is sparse. So every column is n to the delta over 2 sparse. It's a very strong assumption, but let's look here for a second. Well, now we have a very and we had a compressed sensing scheme, and we have a very trivial algorithm for search, right? I just find I compute my matrix H. I then just compute HAB, and then I apply my recovery on the whole product. Right? So if I could compute this measurement matrix, if I could compute HAB efficiently, and I had a recovery algorithm, and every column was sparse, then I can solve MM. Right? There are a bunch of things. We'll slowly get rid of all these assumptions. Okay. So what is the let's assume this is the case. What is the running time of our algorithm? Well, let T1n be the running time to construct such a measurement matrix. Let T2n be the recovery algorithm, like the time to decode any single row or any single column. And let me choose M to be some n to the k, where k is between 0 and 1. And then my running time is just the following function. Right? And so if I can show that this function is less than n omega, I'd be kind of happy. So I want to kind of construct a fine-grained compression sensing scheme that like balances these parameters nicely, and I get a nice one. That's going to be cool. Okay. So let's kind of first prove the following thing, that actually this assumption that all columns are sparse is okay, as we like to call it the Huck lemma, because of Huck. So here's the following statement. I claim that like all the columns, I can just assume that all columns are sparse. This is okay. Why? Because it's kind of the same argument as the sparsity lemma we saw earlier. If every column had sparsity greater than n to the delta over 2, then when I compute the AB minus C, those will all become non-zero, right? So how many such columns can I have? At most n to the delta over 2. So that means my rows of this matrix, I can only have n to the delta such rows. So then my second thing, I just have to work on the transpose, and I only have and each row has like fixed sparsity.
Sorry, what is C prime?
C prime is just on the is the first recovery. So I first compute. Okay, so like now the only thing left to show is that I can actually construct, oops. There we go. That I can actually construct T1, T2 efficiently, and then I'll be happy, right? So we already argued that every column is sparse. All we really have to do now is construct T1 and T2. Efficiently, but even this comes for free actually. So we don't really need much more. So the first thing I'm going to say is I'm going to define what a good linear arithmetic code is in a second. But let's assume such an object exists. I'll define what the parameters of such an object are. Then what we show is that there's like if a code with certain properties that I'll define in a second exists, then such a code implies a compressed sensing scheme for any T-sparse vector with the following properties. That H is a matrix of dimension 2t times n, H can be computed in time n squared, and R runs in time 4 times. So really what we're saying is like to implement such a compressed sensing scheme that we would like to get around. So if I had this scheme, I'm done. So all I need to show is I can actually efficiently implement such a scheme. And we see that if there's a good code, we can implement this, and then we'll see that such a good code actually exists. Okay. So what does it mean to be a good code? It's very simple. I can compute the parity check matrix in systematic form in like quadratic time. Think of this as a random matrix. We can do this even faster. The minimum distance between code words is at most qt. I'll need this for my error correction. And there's a linear time algorithm for decoding my code words with up to m over 2 errors. This is important because like essentially what I'm doing is I'm outsourcing the search problem or like actually computing the matrix to my decoding procedure of my code. So I'm not designing an algorithm, I'm kind of designing a reduction where the code is doing the hard work, right? The decoding algorithm is actually doing the hard work of computing the product.
Why do you need M in this definition?
Why do I need M? Because that dimension is going to be my dimension of my parity matrix. Okay, and so like now, like just generalize these codes are good codes, you can just make this observation. And then when we set T to be n to the delta over 2, we get our nice running bound, and we actually match them.
What is the generalized part of this code?
Oh, just like the parity check matrix, like the first part is going to be the identity matrix. Okay, so we can go back to like next algorithm. So like in this case, we have like a omega 1 delta over 2 1. And we can ask like, so there is a Foster algorithm which is 1 1 delta minus 1. Is this optimal? Is this algorithm actually can we be even better than this? Like can we construct that finer? So clearly the other paper what they show is you can reduce your OSMM to dense rectangular multiplication of this dimension. Can we actually go even faster, right? Turns out that it's kind of already optimal in the following sense, that if I could design a faster OSMM algorithm, that would imply a faster algorithm for my rectangular multiplication. And the reduction is very trivial. I just plug in a bunch of zeros, and now there's an instance where my output has at most n to the delta non-zero entries. So this is kind of tight, right? So like the randomized algorithm is actually, unless like if you improve the randomized algorithm for OSMM, you're actually improving the rectangular error, which is probably hard. Okay. So I guess like, the open question is, can we like kind of, so we know what kind of the optimal deterministic running time should be. Can we kind of bring it down even further from 1 1 delta minus 1 to 1 1 delta over 1? Okay, final part of the talk is completely orthogonal in some ways. So maybe like we have been kind of stuck in our exponent because like we make very, very small progress. Is it possible that like if coming up with a super quadratic algorithm is hard under SCTH? So if I did come up with an algorithm that would like come up with a faster algorithm, maybe that's the reason why like progress is a little bit slower in terms of what the exponent is, right? Is there some kind of, could we have some barrier under SCTH that explains why like the progress on MM is so slow, right, in terms of the exponent? And what we show is actually, it's like a barrier to the barrier, which says that this cannot happen. So if MM was hard under SCTH, here's the following things happen. Either you get like this, like one or two things must hold. So any reduction that shows that MM is hard under SCTH would imply the following things. Either a superlinear circular bound or an explicit construction of a rigid matrix. So let me kind of rephrase this maybe in more SCTH terms. If matrix multiplication is hard under SCTH and set is false, that's what implies a circular bound. So I can just construct a fast non-deterministic algorithm for unsatisfiability. Or there is a kind of quasi-polynomial time algorithm with an empirical, this is a little bit technical, that outputs an n-prime rigid matrix. It's not outputting any useful rigidity, but it's better than all the known constructions. So the idea is just that such a reduction wouldn't in it imply a much stronger sequence of guarantees. So it's not necessarily saying that this is not possible, it's just saying that such a reduction would be extremely powerful. Okay, and I can maybe quickly talk about like how this looks at a high level. Questions before
Do you need this reduction to be like deterministic or something or
that?
no?
I think you need to be deterministic for the NSF part, right? Otherwise you won't get paid.
It is because of this like gap between zero and, zero and linear number of,
No, I mean, the main idea is that I can multiply non-rigid matrices non-deterministically. So if I look at my reduction, we'll see this in a second here. Okay. So let me just quickly give some definitions for people who are set. I'm guessing everybody's familiar with, it's saying that there exists K, so that there's no deterministic algorithm that solves it in minus epsilon for every epsilon. NSET is saying that there's no non-deterministic algorithm for unset. And here's a nice corollary, if NSET is false, then if the MP does not have linear size series parallel circuits. Okay, this is one side of the coin. The other side of the coin is rigid matrices. This is a following explicit object, which is a matrix let me define non-rigidity first. A matrix is non-rigid if it can be written down as a low rank plus sparse matrix. So any matrix that cannot be decomposed that way is considered rigid. Rigid matrices are awesome because we get circular lower bounds, they're just they seem very useful. They're just a nice combinatorial object to have. And we would really like to construct these, get explicit constructions for these rigid matrices. Okay. And again, because I can check if a matrix is low rank plus sparse using an NP oracle, the NP oracle just gives me the low rank plus sparse decomposition. I can verify if a matrix is rigid with an NP oracle. Okay. So now we have these. Any questions about the definitions before I finish the reduction? Okay. So the reduction is actually very easy. Let's assume that there's some gamma where there's mm is n to the gamma hard, right? Where gamma is whatever omega you choose, or whatever value you want to choose. Then I claim that then let there be such a reduction that takes a formula and maps it to a bunch of matrices, right? Now the claim is the following. There are three cases. Case one is that if all my matrices that my reduction outputted were small, then I could just apply my cubic time algorithm, and I get a faster algorithm per set, right? I just multiply them in cubic time. My reduction runs in less than 2 to the delta n time, so I have a faster algorithm for set. So my matrices cannot be all. If my matrices were all small, then that already breaks execution. So some of my matrices must be bigger. If my matrices are big, now let's say all my matrices are big, but they're all non-rigid. What can we do? Well, it turns out that we can multiply there's a non-deterministic algorithm to multiply non-rigid matrices. So I can get the low rank, get the sparse. I can apply sparse matrix multiplication, and I can multiply my low rank. So I have a fast algorithm for non-deterministic, and then again I'll probably break SPH. And so again this is where you get your parameters on the rigidity. And again you'll break NSET, which is case 2. And finally the last case is just the following, which is saying, well, so then one matrix must be rigid. And so now what you do is you try brute forcing all case set formulas and then kind of apply the sparsification lemma, and then use the empirical. So use my reduction as a subroutine on my formulas, and use the empirical to see whether or not the matrices coming out of the reduction are actually rigid or not, because they must exist for in case 3. And that's it.